Hello students, Stride here again. Today we got notes for section 12.3, Newton's third law of motion and momentum. Little introductory example here. We got bumper cars in an amusement park and they collide with another car. Two forces are exerted. Each force is exerting a force on the other. Key question, what is Newton's third law of motion? Here's a little explanation. According to Newton's third law of motion, when one object exerts a force on a second object, the second object exerts an equal and opposite force on the first object. So one of the main things to remember for Newton's third law of motion is this idea of equal and opposite forces. Another way to describe it is action and reaction forces. Remember, action and reaction. And in the bumper car example, the force the bumper car exerts on the other car is called the action force, and the force the other car exerts on your car is called the reaction force. Action and reaction forces are equal in size and opposite in direction. If you press your hand against the wall, your hand exerts an action force on the wall puts an equal and opposite reaction force against your hand. Another example, swimmer pushing against the water. Action force, reaction force is the water acting on the swimmer, causing the swimmer to go ahead. So these action and reaction forces propel the swimmer through the water. The swimmer pushes against the water, and the water pushes against the swimmer. One thing to remember, even though they are equal and opposite, action forces do not cancel. And the reason they do not cancel is they do not act on the same object. The other concept related to this is momentum. Momentum defined to be the product of mass and velocity. And it has a large momentum if it's probably because mass and velocity is large. Object with large momentum, harder to stop than an object with small momentum. If it's at rest, its momentum is zero because its velocity is zero. Formula for momentum, mass times velocity. Mass measured in kilograms, velocity measured in meters per second, momentum kilograms, meters per second. Example question, which has more momentum, 0.046 kilogram golf ball with a speed of 60 meters per second, or a 7 kilogram golf ball with a speed of 6 meters per second. So we just use our formula. Momentum equals mass times velocity. Because velocity is a vector, momentum is also going to be a vector, so this will be another vector. This will be the along with displacement, velocity, acceleration, and then force. Now we've got momentum, a fifth vector. So in the first example, the momentum, let's use momentum equals 0.046 kilograms times 60 meters per second. Calculation of the calculator, and we got 0.046 times 60, 2.76 kilograms meters per second. And for the other one, momentum is going to be 7.0 kilograms times 6.0 meters per second. 7 times 6, 42 kilograms meters per second. So the one with the greater momentum by a lot is the 7 kilogram ball with the speed of 6 meters per second. And here's what the textbook did for their calculations. They rounded to 2.8 and 42, so bowling ball has a lot more momentum. Here we got a thing called the law of conservation of momentum. A closed system. Definition means objects and forces cannot either enter or leave a system. Nothing's coming in, nothing's going out. And in a closed system, the loss of momentum of one object equals the gain of momentum in another object. Momentum is conserved. Objects in a closed system can exert forces on one another. And according to the law of conservation of momentum, if no net force acts on a system, then the total momentum of the system does not change. Some examples dealing with this. And we've got before the collision, we've got a momentum of 300,000 and 150,000. These two things are going in the same direction. They collide. Momentum is transferred from the blue car to the green car. Now the blue one has 150 and the green one has 300,000, but the total remains the same, 450,000. There's one where the green car was not moving, the blue car was. They collide, and all the momentum is transferred from the blue car to the green car. Total momentum remains 300,000. Now the blue car is stationary and the green car is moving. And this time they couple together. Blue car strikes the green car not moving. They hit. Total momentum remains 300,000. 300,000 at the speed of the two cars together, cut in half. Another little example. Class studied the speed and momentum of a 0.25 kilogram ball dropped from a bridge. The graph shows the momentum of the ball from the time it was dropped till the time it hit the bottom. And you can see the momentum kept getting bigger. And as time was going on, that would be because the speed would be increasing because this object would be accelerating due to gravity. At what time did the ball have zero momentum? So time equals 0 would be 0 momentum because it was not moving. So at what time did the ball have the greatest momentum, and what was the peak momentum value? So we just read our graph, and we see that's up here. And the time would be 2.5 seconds, and it had about 6.5 kilograms meters per second. And what was the speed after 1.25 seconds? So 1.25 seconds is going to be right here. So at 1.25 seconds, you see the momentum is 3.25 kilograms meters per second. And to find the speed, we have to take, speed is going to be momentum divided by mass. And so the speed is 3.25 kilograms meters per second divided by the mass of 0.25 kilograms divided out kilograms, and we're left with 13 meters per second. Couple review questions. Stationary figure skater pushes off the boards around an ice skating rink, men's gliding backwards away from the boards. What law explains why the skater moves backwards? And this would be Newton's third law of motion. For every action force, there is an equal and opposite reaction force. Red puck with Velcro on its side is sliding towards a stationary blue puck with the same mass. The pucks will stick together upon contact. After contact, how will the red puck's velocity compare to its initial velocity? And we can ignore friction in this example. So, red puck's velocity will be half its initial velocity and in the same direction. And here we would assume that the two pucks were exactly the same mass. Now, that takes care of notes for section 12.3. That's all for now. Till next time.